Thanks for being here about my talk about Unveiling Network Errors, a deep dive into ICMP Destination Unreachable Messages. So first of all, thanks to ChatGPT for that title. It's always hard to find the correct title, so getting in touch with the real topic, but not too long, too short. I think it's a little too long anyway. However, just a short sentence about me. My name is Johannes Weber. I'm from Germany. I'm working for a systems integrator, SVA, System Vertrieb Alexander. And I'm working as a network security consultant. That is, I'm almost working with network firewall projects, mainly with a vendor called Palo Alto Networks. And my main topics, technically wise, are IPv6 and DNS, and both with security. So last year I gave a talk about DNS, the year before about IPv6, so this time it's solely about the network. I have a blog, it's called Weber Blog. I'm blogging like once a month about technical stuff. I'm still using Twitter and LinkedIn. Okay, so let's get into the topic. I want to talk about ICMP. Who knows what ICMP is? Yeah, everyone knows it. So, but who knows how to use ICMP other than doing ping or traceroute? So it's probably not that many. Robot knows it? Okay. So you're perfectly correct in this room right now, because I'm not going to talk about ping and I'm not going to talk about traceroute at all. But we want to talk about ICMP because ICMP is something that I've called it the unlifted network treasure. Why? Because it's in the network. When you're sniffing, when you're capturing on your firewall, on your router, on your client server machine, whatever, you will see certain types of ICMP messages, but mostly you will simply ignore them because you have never heard about those details. But this is a process within the network where the network itself, through these ICMP messages, tells us what is the current problem we're facing. So what's the motivation to use these ICMP messages? I think it's these two guys. The first one is troubleshooting. Where does this problem come from? So normally when you have a network problem, you're going to start to troubleshoot. There are certain ways, bottom up, top down, and so you probably know them. Can I ping the system? Yes. Can I not ping it? No. What's the problem? So you're trying to troubleshoot. You're capturing, you're looking your firewall policies, monitor logs, whatever. You're grabbing through some syslogs, and you're trying to solve the problem. But please be aware that there's ICMP. So probably when you're looking right at your trace files, you can already spot the problem by simply interpreting these ICMP errors. The second one is housekeeping. Do I see any upcoming problems? So in the end, I will challenge you somehow to capture your own enterprise network. So I'm not talking about home networks, of course, but I'm talking about enterprise networks. So when you're operating a big network, please go ahead and start capturing for 1 hour or for a day or so on certain points and have a look at those ICMP messages, because eventually, you will find some errors that are within your network, and you can fix them before you have a bigger problem, or you can find out that the problem is somewhere else's problem, so that's fine for you as well. So that's the motivation why we want to talk about ICMP. So what we are doing within the next hour is I want to give you some ICMP basics, mainly focusing on the destination unreachable messages. Of course, we want to look at them within Wireshark. That's why we are all here. And I will tell you how to capture. So of course, it's kind of easy. You hit the start capture button, don't you? But when it comes to capturing on bigger points, you need some capture filters. And I think you will miss out these ICMP messages when you're typing the capture filter in a wrong way. So we will talk about how to capture correctly to get all those messages into your trace file. I've done a case study with the NTP pool. That is, I'm operating several servers within the NTP pool. You probably know it, where every IoT device and router gets its time from, something like de.pool.ntp.org. I've made a case study with them on the internet just to show how many errors really are out there. and what kind of stuff. And in the end, I have some challenges, as always in my talks. So I have like some Wiener Neapolitana, 6 times of them. So in the end, I have some challenges for you to get your hands dirty with Wireshark and T-Shark. So let's start with the ICMP basics. ICMP is the Internet Control Message Protocol. Just to have it said one more time. What you all know is echo request, echo reply. I don't want to talk about it at all. This is ping. For IPv6, these are the ICMP types 128, 129. For IPv4, it's the types 0 and 8. One note, everything I say is the same true for IPv6 and for IPv4. So the codes and types differ a little bit, but the concepts are completely the same. So sometimes I forgot about this and I'm simply talking about ICMPv6 because I'm normally using IPv6 a lot. However, please forgive me, everything is for IPv4 and IPv6. So this is what we are not going to talk about. Then for IPv6, we have within the ICMP v6 protocol, we have all this neighbor discovery stuff, like the router solicitation advertisement, neighbor solicitation advertisement. So this is IPv6 stuff. We are not going to talk about this right now. We want to focus on the error messages. But on the error messages, we also have 4 different types 1, 2, 3, and 4. So this is why this list is this way. So the probably best thing you know is the hop limit exceeded or time to live exceeded. So this is a routing loop, aka traceroute. So you know traceroute, if you have a loop between different routers, the IP TTL value is decreased by 1 by every hop. If it reaches 0, the router discards the packet and sends back an hop limit exceeded for IPv6 or a time to live exceeded for IPv4. So this is how like the internet behaves. We are using this trick for traceroute where we intentionally start a ping or a UDP packet or a TCP SYN on port 80 with a TTL of 1, of 2, of 3 to get the routing path to the destination. So this is how traceroute works. Just one sentence about traceroute. Keep in mind that when you're trace routing from a client to a server, and the traceroute only gives you the path to the server, you do not know exactly the reverse path. Because we have asymmetric routing in the internet, this is totally normal. So if you really want to know the complete path from a client to a server, you have to do trace routes on both sides. Because to get the path from the server back to the client, you have to trace route from the server. So trace route from the client only shows you the path to the server, not the full path. Just a side note. I've said we don't want to talk about traceroute. No, I did it anyway. Path MTU, parameter problem, multicast listener stuff. I don't care about within the next hour. We want to talk about destination unreachables. So what is a destination unreachable? We will have to look at this figure for the next couple of slides. So this is like a perfectly well-designed network. You have a client who is behind a firewall. Then you have the internet that consists of multiple routers. And then you have a server, of course. In front of the server, there's another firewall. So from the client, which is the source, on the main session initiation, you got a message that is outgoing on the firewall through the internet, incoming on this firewall to the server, and the server replies. So if any one of these 4 guys, the firewalls and the routers. The firewall are basically layer 3 routers, so simply let's call them routers. If any one of these routers is not able to forward the packet to the final destination, this can be the server when the packet comes from the client, this can be the client if the answering packet from the server. If any one of these routers is not able to forward the packet, it has to discard the packet because he does not know, or he is by policy is not allowed to forward the packet. He has to discard it. And he replies, the router replies with an ICMP destination unreachable to the originating source. So this originating source is not always the client, but it might be the server for the answering packet. So I have drawn some red arrows. So these are the red arrows, the or the errors. However, this is not all situations, but you get the point. If on the blue line, if this router is not able to forward the packet, he will send back a packet, a destination unreachable to the client, or this router or this router. Same for the answering packet. If the answering packet gets an error on this firewall, for example, this firewall will probably reply with a destination unreachable. So this is how the protocol works. So stating the RFC for IPv6 in this case, a destination unreachable messages should be generated by a router. So it's a should, it's not a must. So it's not that every router out there does it, or maybe it's configurable, so you can decide to not send those messages, which is fully fine. But it should generate it by a router in response to a packet that cannot be delivered to its destination address for reasons other than congestion. Okay, so if the router is simply congested, it does not send any of those messages, but only if there's a reason that it cannot deliver this packet to the final destination. For IPv6, it's type 1. For IPv4, it's type 3. So we are talking about ICMPv6.type equals 1 for the destination unreachables, or for ICMP for IPv4.type equals 3. So what are scenarios where this might happen? We will look at 4 different scenarios, and what are the reasons for that. The first one is code 0. So we always have this type. We are within the type. The type is destination unreachable. Now we are digging a little bit deeper. We want to look at the different codes within the type 1 destination unreachables. The first one is no route to destination. So what's that? If any of those routers is not able to forward the packet because of no route, within your internal networks, your routers will always have a default route, or in 99%. So this won't happen within your internal networks because every router has a default route, and the packets are forwarded following this default route. So this can only happen in the default free zone, the DFZ. The DFZ, what we are calling the internet, because on the internet we have hundreds of thousands of routers that get their routes through BGP. So if a route does not exist, the router does not know how to forward this packet. So that is, if a router gets a packet destined for a network which is not in his routing table, he does not know what to do with it, he discards it and sends back this destination unreachable with the code 0, no route to destination. So when might this occur? For a client to a server packet, this might be a typing error. So for example, you're going to SSH to an IP address, or you want to ping an IP address, you're going to HTTPS to an IP address, and you have mistyped something. So you probably want to go to a destination that's simply not routable on the internet. Or if you're DNS, of course you do, that's probably a fault quad A or A record within the DNS. So you're pinging a host name, or you want to SSH to a host name, but this DNS delivers you a wrong IP address, while the IP address is syntactically it's correct, but it's not routable on the internet. So this might occur, yeah? So that some of your internal networks, you have some configured connections, you have done some IP addresses wrong, the server or the internal client tries to connect to the server, but it doesn't reach it. Another scenario is no BGP announcements. So that is, if you're talking to a company which hosts several servers, but for whatever reason, they have an error within their BGP configuration. So the router does not send anymore the BGP updates, so the whole world does not know their prefix anymore. You will see exactly this ICMP destination unreachable message. Interestingly, you can have the same error from from the server back to the client. I'm always talking about this one as well, because normally we only think about the first connection. If the first connection is not working, then we are trying to troubleshoot it, and then we are done. But we are facing many situations where we are hosting a server. So within every enterprise networks, you have your servers hosted, either in a DMZ for public reachable or within your server segment. So always have a look at the server as well. When will the server get this type of no route to destination? Well, if a client reached the server and the server replies, but this router, for example, says, well, I have no route to your client, what can be the case? Probably it's a spoofed source address. For some probably denial of service attacks or stuff like this, the attacker is spoofing random source addresses. Your server will reply to them, but one router along the path says, whoa, I don't know this address. This address is simply not present on the internet. So you will get those no route to destination messages back to your server. Or no BGP announcement. If you're within a session and at some point this firewall router from the enterprise networks stops sending out BGP messages, you cannot reach the network. So again, you will have those errors coming back to the server. So this was the first type out of 4, no route to destination. What's the second one? The second one is called communication with destination administratively prohibited. For IPv6, this is code 1. For IPv4, this is code 13. So this is basically a firewall. If you have a firewall in place and you have configured your firewall to block or to deny or to drop or however your firewall vendor calls it, to discard the packet, you can send an ICMP message back to the originating node that says communication with destination administratively prohibited. Keep in mind, this is only for UDP. Why? Because for TCP, we have the concept of a TCP reset. So if a firewall blocks an outgoing or incoming connection, and you've made the check mark by kind of reset or inform the originating host or whatever, for TCP, the firewall will spoof the server's or client's address and will send a TCP reset in either of both directions or in both directions. For UDP, we don't have this concept of a UDP reset. So for UDP, this is a destination unreachable with code 1 or 13. So for a client to a server connection, this is basically a normal firewall behavior. So we are talking about, probably about this guy. So the client has an outgoing connection, everything is allowed, but this server on port 443 shall not be reached through this firewall, so the session is blocked. The firewall can reply with exactly this one, check mark. On the reverse packet, so this is a little weird because eventually we have a missing stateful firewall. So we all know that firewalls are stateful, but there were some times where firewalls were not stateful. So normally you're opening a connection through this firewall, and of course the reverse packet is allowed as well. But there were some times where this was not the case, so you had to allow the back direction as well. So I've not seen this anymore that much, to be honest. Another one is probably more interesting. It's this one. The answer is longer than the UDP session timeout, for example, for long DNS queries. Fun fact, I've seen exactly this one. So what happened? The client made a DNS query to the recursive DNS server over this firewall. So this firewall has a session, and this firewall will allow back-coming traffic for sure, with the UDP standard default timeout of 30 seconds. So at least this is the one that I'm aware of. For whatever reason, the recursive name server had a DNS loop, and it took him more than 30 seconds to get the right DNS answer. So this is, of course, this was the error, of course. However, when the server finally had the correct DNS answer, it wanted to reply, but this firewall has already killed the session because the UDP timeout was 30 seconds. So in this time, this firewall, again, can reply with this ICMP messages. So the question is, do we as firewall admins, do we want our firewalls to behave like that? Probably not on the internet. Because on the internet, if this is the internet, if this is my firewall, incoming connections, I want them to be silently dropped. So I don't want to reply to anything that is not allowed. Fully correct. But for internal networks, this is interesting. Because, for example, if this firewall is internal and you have an SSH server, and your administration station wants to reach the SSH server. So normally, you're typing SSH, dash, you can log in. So if this firewall now intentionally blocks the SSH connections, but it silently drops them, what happens to me as the network admin? I'm typing SSH, and I have to wait. And I have to wait, and I have to wait. The client retries, I have to wait. And after 10 or 30 or 60 seconds, I get an error stating not reachable. If my intermediate firewall replies with a TCP reset for TCP or with a destination unreachable for UDP, I will go to the SSH server, and 1 millisecond later, I get a boof error, forbidden. So this is perfect, because for internal connections, I directly get the error message that I'm not allowed to reach the destination. I can't reach it anyway, but it shortens the time that I get informed that I cannot reach this destination. So this is why, for example, on Palo Alto network firewalls, you can distinguish between a deny and a drop. And for a drop, you have a check mark that reads send ICMP unreachables. This is exactly this. What it actually does, it does sends this one for UDP, and the TCP is reset for TCP. And yeah, I think it's a good user experience for your internal networks. Next one is code 3 for IPv6 or code 1 for IPv4. This is address unreachable. So that is, your layer 2 address is not resolvable. So the neighbor solicitation, IPv4, or the ARP request, IPv6, sorry, I mixed them, neighbor solicitation for v6, ARP for IPv4 is sent but incomplete. So what is this? The last hop. So you reached the correct network, you are on the router that hosts this layer 3 network, but the last router is not able to forward this IP packet, encapsulate it in an Ethernet frame to the destination MAC address. Because he tries to resolve the layer 3 address, IP address, to the layer 2 address, the MAC address, but it's incomplete because no one replies. So for IPv4, this is an ARP. So when you're looking at the ARP table, you have probably seen this incomplete because your station is on the wrong VLAN or it's down or whatever. For IPv6, it's a neighbor cache where this neighbor solicitation is in the incomplete state. So when can this happen? Well, I think this is quite common if you're talking to new systems. It's not plugged in correctly, it's in the wrong VLAN, probably the host is down, the link is down, you're going to the wrong address. So again, you have mistyped the last octet for IPv4 example, so you're going to try to ping the correct host, but you have a typing error, or again, you have a false DNS record. So these are all scenarios where your server cannot be reached. Again, this can happen on the reverse direction. If your client has reached the server replies, and this very last guy, the last mile, so to say, the last router, is not able to forward this Ethernet frame to the destination MAC address. So probably the link is down from the client. So in the meantime, the client has shut down along with a very short neighbor cache timeout on the router. Okay, so probably this can be a more relevant variant again is the spoofed source address. So if you have an attack for IPv6 or IPv4, where an attacker spoofs random addresses out of a foreign network. So those packets will reach the server does its job and answers the packets, but the last firewall is not able to send them to the destination because those IP addresses simply are not present on the network at all. The last type is port unreachable. So we are walking through the network. You know, at the first one we had no route. On the last one we have reached the correct router, but we were not able to get to the client. So this time we have reached the final destination on the layer 3. We are on that machine for the IP address, which is the message destined for. But now the machine has an unreachable port. So for a server, this is basically if the transport protocol has no listener. If you're trying to SSH to a server that is not listening on port 22, then it replies with a port unreachable. Again, only for UDP. Because for TCP, the server will send a reset. But for UDP, we don't have the concept of reset, so for UDP, it will reply with the port unreachable. UDP, the only two common protocols on the internet where UDP is used is obviously DNS or NTP. For NTP, it's solely UDP. For DNS, UDP is only the half answer because DNS is used over TCP as well. However, these are the two most common protocols that are used via UDP on the internet. So when will this occur? When the client reaches a server, then the server is simply not listening on that port. So maybe the service is shut down or something like this, or it's simply a port scan. So on a port scan, it can be kind of ignored. Of course, that's what a port scan is for, to find the open ports. When the server is not listening, so this is something you can investigate. So coming back to my motivation, you're trying to troubleshoot a problem. When the client comes to you, when your user comes to you and says, "Wow, I can't reach my service, but I can ping it." Of course, but the server is not within your team because you're on the network team. If the server sends back an ICMP destination unreachable with port unreachable, you exactly have the answer that it's not the network which is to blame, but it's the server guys, because the server port is not listening. So that's perfect, because within the network, you already have the proof that it's not the network, but it's the server. So this is what this message is made for. Yeah, I've done a port scan with Nmap, so this is basic stuff. Nmap packet capture. The interesting thing here is that I captured the whole process of the Nmap scan, and within this Nmap scan, you can see that for every TCP port that the server was tried to connect through, it sends a reset, and for every UDP port, it sends exactly this one. So this is normal behavior. Again, when might this occur? On the reverse packet. So that the client has sent a packet to the server does its job, it replies, but the client comes back with a port unreachable. So this is when the client has closed the source port too early. So remember, if a client makes an outgoing connection, it uses an ephemeral random port out of the high port ranges starting by 59,000 something. And of course, it should accept the reply packet to this port. But if for some reason the client has already closed this random ephemeral port too early, the answer that comes back from the server cannot reach the service on the client. So interestingly, we have seen this hundreds of thousand times in the internet due to defective NTP clients. So I have a link here. That is, there were many IoT devices that had an NTP client that was kind of defective, so it sent out hundreds of NTP queries, but it almost always closed the outgoing port immediately. So none of those packets could ever reach the NTP servers. So this is why later on my simple case study, we will see that I have like 99% of those messages generated for NTP were defective NTP clients. But again, if you would capture this within your network, without those ICMP messages, you would not see the error. Because if you're only capturing NTP traffic, for example, you see the request, you see the reply, and you think you're done. If you're looking at those ICMP messages, you can get the idea that there's something wrong with the clients, probably within your own network, because they are constantly replying with those kind of messages. We have two more subsets out of the administratively prohibited that are just a little more detailed. So they read code 5, which is source address failed ingress-egress policy, or code 6, reject route to destination. So I just want to look at this for a second. If we see code 6 for IPv6, reject route to destination, so here it's not an administratively policy, layer 3 policy, but it's a route that is rejected. So this is probably if you have a null route. So if you have some routes within your routing table that are set to send to the def null or to null 0 or however. Yeah. So this is kind of intentionally from the admin, but it's not a security policy, but it's a route entry that comes to the decision of the router that is not able to forward it. So for example, in the internet, we have this bogan list, full bogans and so on. So we have lists on the internet with IP addresses that are not routable. For example, you can use those lists within your routers to omit those packets sent to the next station. Okay, where can you look up all those parameters at the IANA documents? So you probably have seen them a lot. We have the RFCs for the standards, and we have the IANA. These are those documents to look up those types and codes. Okay, let's get into Wireshark. I'm using for this demo and for the challenges later on, I'm using the ultimate PCAP. You probably have heard about it. It's a PCAP with more than 80 protocols in one PCAP. I really love it because I don't have to search for many PCAPs anymore. So whatever I want to show to a client or to a customer or during trainings, I got rid of using multiple key PCAPs for every scenario. I'm simply using this PCAP because almost everything that I'm using in my day-to-day job is within this ultimate PCAP. Yes. So let's have a look at the ultimate PCAP. Is this size? Can anybody read it? Yeah. So for example, for ICMP, as we know, I cannot zoom into the display bar. So I'm sorry, Zake, yeah, you know the feature request. For example, for ICMP, we can use ICMP.type equals 3. So this equals 3 are all those packets that are ICMP, of course, but only for destination unreachables. And in brackets, you can already see what code it is. So if you click on this packet, for example, we have type 3, which is the destination unreachable. But in this time, we have code 3, which is the port unreachable. Fortunately, we can see the code in a reading description, such as port reachable or communication administratively prohibited or filtered. We can read it already here. For IPv6, it's ICMP v6.type equals 1. So having a look at these guys, for example, we have ICMP v6 destination unreachables, or here we have some more. Oh, it's this one. For example, here we have a type 0 with code type 1 with code 0, which is no route to destination. So the big question arises now is, how can I match this ICMP message to the session that brought me to the situation? So here's the answer. When you're looking closely at this packet details pane here, you can see that I have an IPv6, so let's use the very first one here, administratively prohibited. We can see that a source to a destination sent this ICMP message, destination unreachable, administratively prohibited. But now, look at the screen. We have another IPv6 header, another UDP, and another upper layer protocol. So by definition, every ICMP error should add as much as it can from the original packet just behind it. So this is how we can see that the packet that led to this error was this one. From this source to this destination, it was source port 123, destination port, one of the high ports, NTP type server. So that is, we know this packet was an answering packet for NTP, because the query packet would have a destination port of 123. So here we can see that the packet that brought us to this error has a source port of 123. So this was the answering packet from the server. So we know here we probably have a client, for whatever reason, who has closed the port, or we have a destination administratively prohibited. That's one of those funny facts where I don't know why should an outgoing firewall should have a firewall blocking the reverse packet. I don't know. So this was the first part. This is crucial because, please remember the very first sketch that I showed to you. You will get ICMP unreachables from random sources. Normally, when you're looking at traffic, you have a client and a destination. You're filtering for the client and the destination, source destination or address. But these ICMP destination unreachables, they are sent from random routers along the path. You don't know which are those routers. You don't know those IP addresses. So you will see like random IP source addresses out of foreign networks that you're not aware of, because this was the path where something went wrong. So, first to note, within the ICMP messages, you can see the original packet that led us to this error. Fortunately, Wireshark is capable, let me just disable a route here, coloring a route. So Wireshark, let's have a look at some IPv4. It's probably a little easier. Let's have a look at this one. Okay, so I will just have here. So when we look at the very first packet, we have a DNS query, and please note this line here. So normally when we are clicking on any type of packets, you can see this line, which is made from the synac ACK, and you have this check marks and so on. When you're clicking on a packet, you will have a line that shows you if there's any corresponding ICMP error. Why is Wireshark able to do this? Well, because Wireshark knows the session, and Wireshark can match this outgoing packet with the packet that is inside the ICMP error. So this is when you're scrolling through sessions and you have corresponding ICMP errors, you will see it that way. Unfortunately, this is not true in the other way. So when I click on the ICMP error, I do not get a line that shows back to the originating packet. So I have a feature request open for a couple of years. I'm not a technical person, so not a programmer person. I don't understand why this is a big thing. However, we have to deal with it. Next thing to note, and this is really great. please look at the IP addresses. I have this one and I have this one. If I'm doing a conversation filter for IPv4, please know that I'm filtering right now for this IP address, starting with non-92, ending with 35, and this public IP address. However, this filter also matches my ICMP errors. Again, this is probably not new if you were on Zake's filtering session. This filter basically says giving every packet where the IP address equals this one and equals this one. So this is true for those yellow ones, which are my DNS queries, but it's also true for this destination unreachable, even though the first IP header does not show those two IP addresses. But the encapsulated header here shows exactly those two IP addresses. So this is great, because the same is true for the UDP stream. So when I'm filtering for the UDP stream, in this case, for example, it also matches this here. So this is a great feature because you can find for your sessions that you have captured, you can find corresponding ICMP errors. One more thing is when you're doing an analysis with Wireshark, you're probably interested in which packet, which originating source has led me to this error. So I'm using another column, and in this column, I'm using a little trick. Zake has showed us this trick yesterday in a different manner. However, I'm using it for now. I'm using it this way. I've made a custom column. How can I zoom in? Yeah, that way. I'm using a custom column. I've called it original destination that was not reachable. And please note this too. So this is the occurrence. This is the field occurrence. I'm not interested in the first destination, because this is the destination of the ICMP unreachable, but I'm interested in the second destination out of this packet. One more trick here is the OR operator for custom columns. So this custom column gives me the IPv6.destination or the IPv4 destination with a second occurrence. So why is this great? Because in one simple column, I got the answer both for IPv4 packets, the IPv4 destination, second occurrence, for IPv6, the IPv6 address, second occurrence. So when I'm trying to close this one, and when I'm looking again at my ICMP v4 and v6, you can see that for IPv4 packets I have in this column, I have the original destination that was not reachable. For IPv6 I have those one. So just as a little trick to get an idea, because again, if you're only seeing the header IP addresses of the destination unreachables, it probably will irritate you. You're actually interested in the IP address that was tried to reach out but did not succeed. Another program I'm working with is T-Shark. Who has ever used T-Shark at least once? Okay, okay, perfect. That's almost the half. Just 1-2 sentence how I'm using T-Shark. There are many, many more ways that I don't know, but I'm using it solely for mostly this. That is, I want to parse through big packet capture files. So when I'm at the customer side and we have to troubleshoot a DNS problem, and he has captured for 1 week. So we have 20 capture files, each 10 gig. You cannot open a 10 gig file in Wireshark. Well, you can try it, but it's just a try. It's not working because Wireshark is too huge. It simply calculates too many values. So this is what T-Shark is for. With T-Shark, it's a command line tool. You can use an input file, which is the packet capture, which might be big in size. Then you can use a display filter. So to have T-Shark only look at these packets for which this display filter is correct, for example, UDP stream or DNS or ICMP stuff. And then you can additionally, you can either then save the output. So if you have a big capture file and you're only interested in a couple of packets, you can use T-Shark, build your filter, save it as a new capture file, then it's probably just a couple of 100 MB in size and you can open it. Or you can use T-Shark with the option -t fields, and you can tell it which fields you want to extract. So, for example, if you're only interested in the destination nodes for which you got some ICMP errors, you can build your filter. You can tell T-Shark to extract to output only this value, for example, an IP address. And then you can use some other well-known Linux, or you can use them on macOS for sure, or on Windows, like sort and unique. So if you have a list that is random, you can sort it, boof, and you can unique it so that double entries are omitted, and you can count the errors. Or you can count the occurrences of all of these unique IP addresses, for example. So when I'm using T-Shark, for example, we can have a look at this one. So I did a big capture for NTP traffic. So within this capture, it was like 10 gigs in size, but I was only interested in the ICMPv6 errors. So my display filter for this T-Shark query was, please only look at ICMPv6. And then I was -t fields, I was only interested in the ICMPv6 type and in the ICMPv6 code. So that basically is, I want some statistics. I want the statistic out of this capture file. How many times have I seen which type and which code for ICMPv6 messages? I want you to sort it, and I want you to unique it. I want you to count every single packet alongside with this. So the output is this one. So the text, I've written the text by myself on the right-hand side. So what we have here at the first glance is the type, because that was the first parameter I wanted to as the output. And the second is the code, because this was the second column I wanted it. The very first column this one, came since I counted it. So what we can see here right now is that, for example, the no route to destination, which is ICMPv6 type 1 with code 0, occurred 385 times with my packet capture. So, and so on and so on. So I got in basic statistics. So, of course, this is just a first clue, at a first glance of my whole packet capture file. So in real life, you would not only filter for ICMPv6 or ICMPv4 in general, but you would filter for, let's say, for client network. If you have captured on your firewall and you're interested, am I seeing any errors for this client network? You can filter, you can display filter for the IP addresses sourced from your client network, and you get a statistic. Or you're operating a server on the internet and you're searching for ICMP errors solely that have reached this server, and you get a statistic. So this is how I'm using T-Shark. Of course, this is just the basic statistics. So know that when I know that everything is fine, I can go to the next server or can go to the next client pool, for example. But if there's something wrong, then of course I have to fire Wireshark, have a look at those packets in detail. The next question is how to capture. Well, basically, every one of you can hit the capture button in Wireshark, that's for sure. But when you're filtering, when you're capturing on a server, for example, or on an intermediate router or firewall, you're probably doing something like this. You have a basic capture filter. It's not a display filter for Wireshark, it's a capture filter. You basically have something like this, host A and host B. Why? Because this is what you're interested in. You want to troubleshoot a certain connection. In the ticket, you have the client IP address, you have the server IP address. What are you doing? You're trying to capture those packets that are between this client and between the server, don't you? So what's the problem on this capture filter? It loses ICMP errors. Why? Because those ICMP errors are sourced from random addresses along the path. So this is a big deal, because I've done this for years. So I ended up with captures in Wireshark from which the network would have told me what the error is, because it has sent ICMP messages, but on the very first step, when I took the capture, I already omitted all those ICMP messages. How should a display filter look like? So, every time, whenever you're capturing, please add an or ICMP or ICMP6, or one of both, the one you're troubleshooting currently. So for example, TCP dump -e interface, and then you have something like, your first filter can remain the same, simply put it in brackets, and then add an or ICMP6 or an or ICMP. So for IPv6 is ICMP6, it's not ICMP-v6, it's ICMP6 without the V for the capture filter. However, so yeah, please use this one whenever you're capturing from now on, because we have heard in other lessons, if you're capturing the wrong stuff, you cannot solve some kind of problems. Later on, you can filter within your captures, using a display filter for sure, but if the original capture already misses the packets you're interested in, when you won't find them. So this is how you should do it. The next question is, why do I have to capture by myself? So probably you're asking, well, Johannes, this is nice stuff, but I simply can click this button on my IDS IPS firewall server, and then I have an ICMP analysis. No, you don't. So the problem is, neither routers nor next-gen firewalls provide any type of ICMP analysis. That is, you have your policies, you have your monitor logs. Within your monitor logs, you can see whether or not you have coming in and reverse packets, TX, RX counters perfect. But you do not know whether everything works correctly. Coming back to the scenario where my NTP server has answered, in my firewall log, I can see an NTP session with sent and received packets. From a firewall perspective, everything is fine, but it was not the case. So I'm sorry, you have to do it yourself. I'm not aware of any box where I can click on a session and it says me, exclamation mark, be careful, we have seen ICMP errors concerning the sessions. I'm not aware of. So you have to do it by yourself. The next question, oh no, let me just point to the next one. At least NTOP and G. Fun fact, Luca Deri, the creator of NTOP and G, exactly now gives a talk in the other room. At least NTOP and G shows me some basic statistics of ICMP messages type in code, and I can dig into them. And for example, here I clicked on the flows, communication with destination, and can see which sessions send me back this error. So, for example, you can use NTOP NG within your network, but you're probably not doing it everywhere. One more question is, do my firewalls deliver ICMP packets correctly? So again, think about my sketch. The firewall on the client side allowed an outgoing connection, and within the session table, it will allow the reverse packets, where the destination source and destination IP addresses and ports are simply swapped. Does my client-facing firewall allow ICMP errors back to the client? Probably. I know some vendors that are doing it. I know some vendors that are doing it not. So please check your firewalls, for example, because for the firewall, it's not that easy, because again, the firewall has to read out through the ICMP packet, has to find the second IP header, and has to match this one against the session table, and then should forward it to the client. A randomly generated ICMP packet from a random source should not be forwarded by the firewall to the client. Or what? Yeah, so the question is, if you have a proxy in line, then the proxy will receive those messages. Yes, it will, because an explicit proxy, yeah, exactly. So with an explicit proxy, the proxy is the source and destination from the server's perspective, and you have another session from the client to the proxy. That's correct, yeah. I forgot to say, if you have any types of questions, please come to with the, yeah. Exactly. So the question is, how can you investigate whether your firewall behaves like this? You can simply, in quotation marks, you can simply capture in front of the firewall and after the firewall and compare the capture files. Exactly. So if you are using all those stuff and you're finding no errors within your network, probably you have to check whether or not your outbound firewall sends those messages back to your client. Exactly, that's how you're doing it. Or the proxy, exactly. Another question is, are packet captures on firewalls capturing ICMP? So again, the same question. If you have a filter criteria and you're capturing on your firewall, for example, you have to do the same. So you have to do an OR ICMP, for example, to capture those packets as well. I've made a case study. So fun fact, this was how I came to this topic. Because I am operating a couple of NTP servers, so on the NTP pool. I think everyone should know about the NTP pool. Yeah, well, these are voluntary servers on the internet that are delivering the time, and you can use some of those host names like pool.ntp.org or so to get your time from. So I'm operating this one. This is a Meinberg LAN time M200. It's reachable under ntp3.weberlab.de. It's IPv6 only. However, for the time of my case study, I made a dual stack, so I made it with IPv4 as well. So this IP addresses, IP4 and IPv6, they appeared, or they're still appearing in the pool in different zones. That's the add zone, Europe, and DE. Just a little detail note for all those pools that you have only the one with the 2 in front of the host name. This is the only one that delivers quad A records. So the one-to-one comparison from IPv4 to IPv6 traffic is probably not that fair, because depending on how the clients are using the NTP pool, some of them, though they are dual stacked, won't ever receive an IPv6 quad A record back because they are doing it that way. Okay, however, so let's just have a look at the stats. For IPv6 and for legacy IP, which is IPv4. So for the number of packets, you can read the numbers here. NTP packets per second, unique sources of NTP packets. Oh, this one is interesting. Unique source addresses of NTP packets. We have a higher percentage of unique sources per NTP packet than compared to IPv4. Why? Because of source nuts. So if there are a couple of different IoT devices behind the same public reachable IPv4, they are nutted, and so percentage-wise, I see more unique sources for IPv6. Okay, so the interesting part comes now. How many NTP sources have I seen that caused ICMP errors? These are 30K versus 96K thousands. So what's the percentage of failed NTP sources? 4.5% for IPv6 and 2.8% for IPv4. So this is huge to my point of view, because every IoT device, every router, every Linux distribution uses this pool. So I initially thought, oh, I want to do some statistic on my NTP stuff. And it came out that roughly 5% led to an error. I was like, what? This is normally when you have a network, I want the network to be reliable as much. I want statistics from 99.99999, for example. I don't want something like, oh, the network is reachable in maybe 95% or so. So I digged a little deeper into what caused the errors. So here for IPv6 and for IPv4, I made the statistic what kind of error, so these are exactly the 4 cases I showed to you, and I added the time exceeded one, am I seeing on this within these 66 days, so I have done it for almost two months. So the answer is, first thing to note, every single error was present on both protocols. So again, this was the perspective from my server. So these are all clients that have used my server, so at least they are functional on the IP layer. They could use their DNS, they have a working NTP client, but still I've seen any type of error, which was my server replied, of course, and I got the answer from one of the intermediate routers back to my server. I saw every single case. However, we have some huge hotspots. For IPv6, we have the destination unreachable, address unreachable, with almost 90%. So the address unreachable, case number 3, is the one where I have a neighbor discovery problem, where I got to the right router, but this router was not able to find the MAC address of the client. So I'm not fully sure why this is so huge, because eventually those clients do not have a working IPv6 stack at all, because they are sending out IPv6 packets, but they are not replying to neighbor solicitations. So this is the ARP request for IPv4. They are not replying to neighbor solicitations. So either I got hacked or I got spoofed by many source addresses that are not on the internet, but at least this should have been source addresses with a valid address, with a valid and routable layer 3 IPv6 networks on the internet. So I more or less think that these are defective IPv6 stacks. Sake. The question is whether it could be temporary IPv6 addresses that change during the transmit. I don't think so, because it's simply too much. So if a temporary address is not preferred, it's still valid for, like, I think the 7 times of the preferred lifetime. So a temporary address is more or less 1 day preferred and 7 times valid. So it should not be the case, because on the 2nd day you're already sending with a new address, but not in this high percentage. Yeah. For legacy IP, for IPv4, I have seen many port unreachables. So this is the case where the answering packet from the server reached the final destination. However, the final destination, the NTP client that queried my NTP server, simply said, no, I don't want to accept any ports, any packets on this source port. So again, these are probably those defective NTP clients that other people around the world have seen during that period, or are still in the internet, where they're not behaving that way. So these statistics is not a general view of all the internet has some problems. It's just for my NTP servers, of course. I just wanted to show how you can use this data out of your network. Oh, what time of the day did I see these errors? Yeah, that's an interesting question. So that comes to, I think, to this slide. You could analyze so much more with the data. So at some points I stopped investigating my case study. You could do so much more. For example, you could investigate the time. Yeah, even with Wireshark, so you can have some I/O graphs during what time period I can see these errors. I've not done that, but it's a good idea. I've done something different, and I have analyzed, again with T-Shark, I've looked at ICMP errors, and I wanted to know what are the NTP clients. So what are the IP addresses that queried my NTP server replied, and I have then seen errors. So these are the top 4 public IP addresses that have reached my NTP server. So, and this is a lot. This is the counter. So what happened here? We probably have some routers that are not doing the source NAT for its own packets. Because when I looked at it with Wireshark, I have seen those source addresses from the ICMP sources. So these are the routers that send the sources. When I did resolve host names, I got this. So TIPconnect.de, this is the Deutsche Telekom. So these are all residential ISP connections out of the German region. This is for Vodafone, another competitor. So there are a couple things to note. At first, these are probably all routers that are doing their source NAT, but only for IP addresses within their network, but that have not done the source NAT for their own sourced NTP clients. The second one, Sake is does not fully agree. The second part is, why is this RFC 1980 space rooted on the internet at all? So the thing is, different routers finally said they are not reachable. So that is, from my perspective, I had different routes to this private IPv4 address space during the time. So there's something wrong with the BGP routing out of this provider for RFC 1980 addresses, because obviously you should not, routers in the internet should have a discard route for RFC 1918 address space and should not try to route it on the internet at all. Yeah, this happens when you're digging into stuff like this. Yeah, please, Sake, go ahead.
The original source addresses don't look like, they're not either 1 or 254, so they look like client addresses from the client pool. So what I think is happening is that the ICMP Unreachable message, which has an original IP address and it is in the second header, the router does not the second header. So it does not the content of the ICMP packet.
Okay, so Sake basically says that these are probably not the originating sources, but behind the router. Yeah.
Which this is the second address, and that's not translated.
Okay, yeah, so that might be that this is not translated. So the interesting part is that these are exactly those 4 guys, 100 to 103, and there's the 104. So I have no idea. So maybe I have to do some further investigation, but it looks like it's not a simple error. So this is some problem, some generic problem with some router brand. Yeah, I'm not fully sure what the error is, to be honest. Yeah. Okay, so this was the theoretical part. Now I have some challenges. So I challenge you to use the ultimate PCAP. Only if you're interested. So I have 6 questions, and I have 6 time traditional Wien manner. I have 6 questions. I give you a couple of 1-2 minutes per question, and then I will show the answer anyway. So, but everyone who is interested in participating and trying to search through ICMP errors is welcome. Are there anyone who is interested? At least, yeah, Robert, okay, cool. Okay, so do you don't have a laptop, you have no choice, right? Sorry, if you have no laptop, yes, you have to ask your neighbor, yeah. I don't know, is there a portable Wireshark for iOS on the market? Yeah. Okay, so the first question is concerning, sorry, just stop. Please make sure you have the most recent ultimate PCAP, because I made an emergency change on the PCAP last week. I'm sorry. So you have to download the most current ultimate PCAP. It's a timestamp with November 2024, November the 1st or so. First, yes, okay. So that's because I'm constantly adding packets to the ultimate PCAP. So the UDP streams, for example, don't stay the same. So if I'm adding packets before and packets be after the current timestamp, all those UDP streams get mixed. So the first question is concerning UDP stream 1177 and 1178. You should see 2 DNS queries and 2 ICMP errors. So the question is, it's the same query, but it's different errors. Why? So you should see something like this. Yes.
I would say in the first case that the server had a closed port, and in the second case was filtered by.
Exactly. So this is exactly correct. So you're the first one. So unfortunately, you're not allowed to answer any more questions for today. But okay. So the answer was we can see 2 DNS queries from the same source to the same destination. But then the first time we're getting back a destination unreachable, port unreachable. So the answer here is the server simply has a closed port. So this server is not replying to DNS queries at all. In the second case, we can see a communication administratively filtered. So in the meantime, there was a firewall in between that blocked outgoing DNS queries and sent back an ICMP unreachable message. So this is why we have those 2 different ICMP errors. Correct. Next one, again, we want to look at 2 UDP streams. UDP stream 249 and 251. So it's basically the same question. Compare the errors. What are the differences? What are the differences on these 2 errors? And more interestingly, what's notable on the second packet? Yes?
The first packet, the route was just not found, so it did not reach the destination.
Mm-hmm.
In the second case, the route was explicitly rejected, and the thing is that the destination is in FDEF, which is not routable.
Exactly. So you're perfectly right. The first one is a classical no route to destination. So in the first case, you can see here an NTP query. My server answered to this destination. But along the routing path, some of the routers said, well, this client you're trying to reach is not routable. So for whatever reason, was either a spoofed source address of the client, or in fact, the network of the client was lost in the meantime. So the BGP routing disappeared, and one of the routers replied with no route to destination. Correct. The second one is a destination unreachable reject route to destination. So this is the type where it's not a policy, and it's not that the route does not exist, but is that the route is explicitly rejected So it's a routing decision, not a firewall admin decision. It's a routing decision. So why? Please have a look at the source address. It starts with FD. So this is evil because FD is out of the multicast range for IPv6. And the standards for IPv6 clearly read it's not allowed at all to source a packet from a multicast address. So this is a completely broken IPv6 stack that sent out an NTP query from a multicast address. Interestingly, this packet was not blocked along the path, neither on the outgoing firewall from the client, nor on my incoming firewall. It was not blocked on my NTP server because he replied to a multicast address, which is ridiculous as well. It was even allowed by my firewall outgoing. At least one of the routers then said, wait a minute, you're trying to reach a multicast address. That's not how it should work. So this is rejected route to destination because exactly this packet here is from a multicast source. Thanks for that. Next question. So this is a little beyond the solely ICMP stuff. UDP stream equals 1178. You should see an administratively blocked session, but the question is how far away from the client was the firewall that actually blocked the session? Oops. So again, we are seeing one of the DNS outgoing connections. Exactly. So the answer is it is directly connected. Probably it's a glue that the IPv4 address could be out of the same range because it's 33 who sends back the error. But exactly, we can look at the IPTTL. So this is a great trick because for ICMP messages that are sourced from a router along the path, it probably has another TTL value compared to the original packet. So in this case, I captured on the client, I've seen that the ICMP packet came back with a time to live from 64. So the mostly used starting points for IPTTL, so for hop limits, are 64, 128, 256. So this is probably the first firewall who sent back this packet because the TTL was not decreased by 1 at all. So
You're showing wrong TTL. Was 128
I think I've clicked on the error and I wanted to see. So this error packet from the firewall back to the client has a TTL from 64.
Yeah, but the encapsulated UDP, the IP packet has also the time to live 128.
Ah, okay.
There would be
Oh,
between, then it would be reduced decrement.
yeah, okay. So correct. Here, I think both have solved it in the same way. So if there would be some other routers in between, this packet as well as the ICMP packet would have seen some decreased IP values. Yeah, perfect. Next one. It's an IP address filter. I give you some time to type it. So it's basically the same question. So Uli, I'm sorry, you're not allowed to answer anymore. The question is, how many hops into the foreign network was the originating host located? Compared to the original. Yeah. Sorry? Last hop before the client. This is correct. So let's have a look at the IP-TTL values again. So the very first packet we see is an NTP query from this source. For this, we have a time to live on 52. Interestingly, the destination unreachable host unreachable has the same source address. But now we can see a time to live of 53. Why? Because this is a router who does source NAT. So the original packet, which got network address translation on this router, the original packet was one more hop away because this router who does the NAT has already decreased the IP-TTL value. But when the router itself, from the same IP address as I can see it here, answers, I have a TTL one above. So the answer is correct. So this client was one hop into the foreign network. So I want this as it's a little beside ICMP, but I want to show that there are fields in the IP protocol that can be used for interesting stuff. For example, source NATs. So with this IP-TTL, when you can compare it to different packets, you can have a glue how many routers in internal networks were in between. It's correct. Okay, so it's getting a little bit more complicated. So I want you to use T-Shark. Maybe I will just throw away the question for a second. So please try to get T-Shark running. So you could either do this on a Linux machine, so this is what I'm doing, or you can do it on Windows as well. I'm not a Mac user, I'm sorry. It's T-Shark also. On Windows, okay, on Windows, you can use T-Shark out of the installation folder for Wireshark. So you can use your command and can navigate through the Wireshark installation folder. Or there's a trick, you can add the environment variables and add this Wireshark thing. So this is not for today, but when I'm using T-Shark, I can use T-Shark anywhere within my Windows operating system because I've added it that way. However, for now on, it's probably easier if you're on a Windows machine that you're simply copying the ultimate PCAP into the into the installation folder just for now. Okay, are there some people ready for T-Shark? So the question is, investigate all ICMP v6 destination unreachables. So this is how you should write the display filter. And then, which codes occur and how often? So I will try to make this one as well. So the first part is you have to use T-Shark -R to read the ultimate PCAP. The second part is that we have to use -y in uppercase to have the display filter. So for the display filter, I want ICMP v6 destination unreachables. So this is type 1. So the display filter would be ICMP v6 dot type equals 1. If I'm now hitting enter, it basically gives me all the packets. But this is not what I'm interested in. I'm interested in some stats. So I only want -t fields. This is, please only give me the following fields, -e. So with -e, I can now specify which fields I am interested in. So in this time, I'm interested in the codes for ICMPv6. So for ICMPv6, it's ICMPv6.code. If I'm now hitting enter, it looks something like this. So for all ICMPv6 destination unreachables, I'm getting simply the code in a not sorted order. So again, I have to use two little tools. What tools am I using? Sort and unique. So I'm using sort, because when I'm now hit enter, I get the same list, but it's sorted. And I want to know how often those codes occurred. So I'm using unique. Unique omits doubles, but I'm using omit with -c. Anyone? You already have one? Philip? No? Okay, so if I'm now hitting enter, here are the answers. So it should look like this. So on the second column, I have the codes I could now correlate to the errors. And in the first column, I have the count. For example, I've 12 times I've seen code number 4. Is anyone having this output? It's super slow on the Mac. At least you tried. Yeah? Okay. So I have one. I don't want to eat it myself. Or do you have a question? No. Okay, so the last one. Maybe I will skip the last one because we are out of time, okay? Let's come. Whoever thinks would have solved the last one can get this one. Okay, so let's come to a conclusion. So ICMP provides useful information. So I think this should be, you keep that in mind. With ICMP, we have answers directly on the network. We simply have to look at them. We have to capture them, and we should know how to interpret them. So, however, analysis requires special tools and tricks. So you have to do it by yourself, and you have to look at it by yourself. The recommendation is capture and analyze on a regular basis. So on a regular basis is not once a month, but maybe once a year. Maybe you can do a reminder for yourself. Last Friday in January, you're trying to capture just for 1 hour and just analyze. It's not that hard. It's in the presentation. You can use almost the same filters and the same stuff for T-Shark, just to get an idea whether or not it's your fault. You can capture on client segments, you can capture on your server segments, and you can get an idea of how many errors are within your network already. And of course, you can use it for troubleshooting. So whenever next time you're using TCP dump, please please add in or ICMP, and you're done. Okay. Feedback, highly appreciated. You can use it on the link as well, on the agenda, or you can scan this QR code. I have some stickers. I have some left for IPv6 and NAT, and the one quite new, a PCAP is worth 1,000 words. You can use the ultimate PCAP. So I have still some stickers here, which you can grab.